All right, hello astronomy students. This is the second video that I'm going to make on chapter 1. I don't know, maybe I'll make a third. If I make it really long, then, you can stop it and start it again. You don't have to watch it all at once. I'll try to be exciting. I'm not sure what I can do to be exciting. I'll do my best. Okay, first one, we talked about this picture. So let's move on from this. You know all these distances, lots of good stuff. They talk about some things here about the closest stars. You really should know about the closest star. I mentioned it before, but let's go into more detail. You can't see it from here. It's called Alpha Centauri. Alpha because it's the brightest, the alpha star. Alpha is the Greek letter A, or Latin. No, Greek letter A is alpha. And that A is like first, right? So it's the Alpha Centauri, the brightest star in the constellation Centaur. You have to go south to see it. But it gets confusing. Alpha Centauri is actually 3 stars. There's 3 stars really close together. When you look up in the sky from Hawaii, you see 1 star because your eyes can't tell there's 3. But with a really good telescope, you can tell there's 3. And I'll show you a picture of that here. Okay, here's a picture with a good telescope of Alpha Centauri. These are the 2 stars you see with your eyes. They look like 1 because it's so far away. But right here, and I don't know if you can see, there's a red circle around it. Maybe you can't see it, but I'll circle it right there. It's a little red star. And I just put a black dot there, but right there is a little red star. That is called Proxima Centauri. Proxima means close, and I probably should have capitalized it. Seems like they capitalize the name of these things. Proxima Centauri. Proxima means close to, like approximate is close to the right answer, and it's in the constellation Centaur. It is the closest one to us because we're somewhere down here. Here's the sun. Actually, it's really far away. On this scale, if this is how big these things are, it would be like, oh heck, I don't know. It would be really far away, like miles and miles and miles down below my feet. Actually, probably more than that, thousands of miles below my feet. Okay. But anyway, I can't draw that here. So there's the sun, and there's us going around the sun. So the closest one to us is Proxima Centauri. These guys are a little bit further away. It turns out Proxima Centauri is about 4.24 light years away, a little bit closer. And then these guys are about 4.37 light years. They're both about the same. So when people ask you what the closest star is, you can say, well, the one that you can see is called Alpha Centauri because you really can't see this one. But this one is the closest star. It's just really dim. It's red. It's not very bright. You can't see it with just your eyes. So really you could say Proxima Centauri. That's probably the most technically best answer. But Alpha Centauri works because they're all, Alpha Centauri is named for all 3 of them. It's a triple star system. And the 2 bright ones, which you see with your eyes, you get the idea. Complicated question. But that's how it works. So you should know something about this. You should know Proxima Centauri, and Alpha Centauri is the name of that one there. Okay. Wow, this is weird. It goes back and forth. Let's go back to here. Yeah, right here. Okay, so Alpha Centauri and Proxima Centauri. Okay, so that's the closest star. So what else should we know here? Also within 10 light years, there are about 10 stars. There are about 10 stars closer than 10 light years. That's pretty cool to know. They say that right here. Within 10 light years, one of them is obviously Alpha Centauri. The other one is Sirius, the brightest star in the night sky, which we can see from here is called Sirius. I know it's less than 10 light years away. There's only about 10, but within 100 light years, there's about 10,000. So within 100 light years is about 10,000 stars. When you look up in the sky, those are most of the stars you can see. There are a few further than 100 light years away you can see, like Betelgeuse and Rigel, but most of them are within 100 light years. Those are like 500 light years away and stuff. So you can only see, within maybe 500 light years up there. And at any one time at night, you can see about maybe 2,000 stars. Okay, that's about it. You think, oh, billions of stars. You can only pick out, if you were to count them, there's one, there's one, there's one, maybe 2,000 stars. And actually, probably even on the best night, 1,000 stars, because it's hard to see all of them, unless you have a really dark sky, you're up in the mountains in a perfect night. However, there's a lot out there because what you can see is the Milky Way, the galaxy that we live in. And but you can't pick them out individually. You just see like a glow. Individually, you can maybe count 1,000 to maybe the best night 2,000 stars. Okay, so those are numbers you should know. The Milky Way has about what am I saying here? The Milky Way is about 100,000 light years across. That they say there encompasses the entire Milky Way. This is a picture not of the Milky Way. We don't have a picture of the Milky Way. It's impossible to take a picture of the Milky Way because the Milky Way, they think, looks like this galaxy. This is a galaxy that's a real picture of a galaxy they think the Milky Way looks like. So the Milky Way, if this was our galaxy, it'd be about 100,000 light years across, roughly. You know, it's a nice round number. Again, in astronomy, we use a lot of round numbers. So 100,000 light years across, that's how big the Milky Way is, roughly. We can't take a real picture of it because, think about it, if we take a real picture of it, we got to get a spacecraft somewhere out here to look down on it. That might be, what, 50,000 light years away? 20,000 light years above it to actually look down and look at it? That means it would take light 20,000 years to get to here. Well, our spacecraft maybe travel 1,000 times slower than light, actually more than that, times slower than light. It would take millions of years to send the spacecraft here to take a picture. So clearly we can't take a picture of the Milky Way, but this is our best guess. It's actually, this is the one that they think our Milky Way looks like. 100,000 light years across, takes 100,000 years for light to get across our galaxy, the Milky Way. Yes, okay. Oh, and how many stars are there in the Milky Way? Well, it's hard to count them, right? The best guess these days is inside the Milky Way, there's maybe about 400 billion stars. There's a lot of disagreement on this number. Really, it goes anywhere from 100 to 400, depending on what video you're watching, what book you're reading. The latest estimates seem to be more in the higher end. Seems like the best data now is maybe 400, but a lot of people still say 100 or 200, and really, they're all right. So really, we could say 100 to 400 billion stars, because no one knows for sure. You can't count them all. Why can't you count them all? Well, because first you got to be able to see them. And if we live way over here, we live about a little more than halfway. We live about 3/5 of the way out. Okay, so if this is 50,000 light years, that would be half the galaxy. We live about 3/5, so we live about 30 billion roughly. I think it's really 28, but we live about 30 billion light years from the center. So we're like right here, about 30,000 light years from the center. There's us. 30,000 light years from the center of the galaxy. And since we're right here, we can't see these stars very well. They just have to guess what they think is there because there's a lot of bright stuff in the middle blocking it. Plus, there's a whole lot of gas and dust. We actually can't even see the brights in the center with our eyes. It should be really bright because in between us and there, there's a whole bunch of dust and gas that blocks the light. If you look towards the constellation Sagittarius, you'd be looking, so if here we are, the constellation Sagittarius is right here. It's supposed to be like an archer, looks more like a teapot in real life. That would be the direction of the center of the galaxy. It should be really bright, but instead it's actually kind of dark part of the Milky Way because it's there's gas and dust blocking it. Okay, so we live 30,000 light years from the center. We can't see this very well. We can't see these stars, so we got to guess. Now, how long would it take to count 1 billion? Let's say you counted 1 a second. Okay, if you counted 1 a second, like you're counting 1, 1,000, 2, 1,000, 3, 1,000, in a year, non-stop counting, no sleep, you would count to 31.6. There are 31.6 million seconds in a year. So if you counted all the way to 31.6 million, 1 a second, it would take you a year. So you're a little kid, and you want to count to 100, you're all proud of yourself. I can count to 100, I'm going to count to 1,000 now. Maybe some of you made it to 1,000 and think, oh, I'm going to count to 10,000, I'm going to count to 1 million. Well, you probably didn't count to 1 million because that'd take you 1/30th of a year. So anyway, if you were to count nonstop for a year, 1 a second, you can't even say like 3,429,300,000. You can't even say the number in a second. But let's say you did. You would count to 31.6 million in 1 year. And that's rough. It's 31.55. It's close enough, right? We just need to get close enough. So let's write that out. So 31.6 million. So 31,600,000 seconds per year. Seconds per year. Okay. How long would it take to count to a billion? Now let's play rough math here. Again, close enough. 3 of these, 3 times 31, it's kind of close to 33. So that would be 100 million, right? So that's 1 year. So 100 million, it'd take you about 3 years, a little over, but close enough. It'd take you 3 years, 3 of those to count to 100 million. Well, a billion is 10 of these. 10 hundred millions is a billion. So it'd take you about 30 years to count to 1 billion. Well, they think there are about, let's do the 100 because it's easy math, 100 billion stars in a galaxy. So 100 billion times 30, 1 billion should be 100 times 30. So it'd be 30 times 100, add 2 zeros, so 30 with 2 zeros. So about 3,000 years to count all the stars in the galaxy. And that's the small end of the stars, right? If it's 400, it'd take you 12,000 years. Anyway, we're not going to be doing that. Takes too long, right? Takes too long to count to a billion. A billion is a lot. If you were to count, if you're a billionaire, you had $1 billion, it would take you 30 years to count out your dollar bills. 30 years of counting dollar bills, 1 a second, so no sleep. Okay, these numbers are big. Oh, the other cool thing is, if you take all the sand okay, no, the way it works is, and we've done this in class actually, let's say you had a grain of sand for all, I think we did 200 billion, for all 200 billion stars. So you had 200 billion sand grains. And actually, we've done that in class. I've given out little pieces of sand to people. You're lucky you don't have to do that. We have counting sand, and we measured it all out, the volume. It ends up filling a space about 10 feet by 10 feet by 10 feet, like a corner of the classroom. Okay, imagine a box 10 feet by 10 feet by 10 feet. That would fit all the sand, 200 billion sand grains, or so about the number of grains of sand for all the stars in the galaxy. So imagine that amount of sand, okay? 10 by 10 by 10. That's how many stars we have in our galaxy. That's a heck of a lot of sand, right? Imagine going to Barn Beach or something and digging a hole 10 feet by 10. All that sand you dug out. Each grain is a star in the galaxy. Now, they think there's about 200 billion galaxies. Just works out about that way. About 200 billion stars in our galaxy. They think there's about 200 billion galaxies in the Milky Way. There's not that amount of sand. Sorry, not in the Milky Way. In the observable universe. In our universe, we are one of about 200 billion galaxies. There's not enough sand on all the beaches of the Earth, of everywhere on the Earth. All the deserts, take all the sand grains on the Earth. There are not that many sand grains for every star in the galaxy. I keep saying that wrong. Star in the universe. The galaxy, we got a corner of a room, right? 10 by 10 foot. But there are not 200 billion 10 foot by 10 foot spaces and that much sand in all of the Earth. So imagine all the sand you can think of on all the beaches in the Sahara Desert and everything. There's more stars in the universe than there are sand grains. Crazy, right? It's a big universe. That's a lot of sand. That's a lot of stars. Okay, so that's something, one way to visualize big numbers. You can think about sand grains and stuff because they're so big. You know, yeah, you can't count that big. All right, that's good stuff. Stuff you should know. So let's see. 31. Scrolling down here. What else do we got here? So galaxies, yeah, we're about 30,000 light years, they say there, like I did, about 30,000 light years from the center. Okay, that's all very good. Here's a picture of the Milky Way. This is with just like a camera, a really good camera, where you leave the shutter open, you can get some colors. You can see this late at night, the streak across the sky. Again, it should be bright, but the dark areas are where there's clouds of dust and gas blocking the stars. When you're looking at the Milky Way like this, you're seeing billions of stars, but you can't pick them out individually. The only ones you can pick out individually, maybe, like I said, about 1,000. Okay, so there's someone looking at the Milky Way. It's awesome. let's see, what do they say here? So, oh, we'll talk about this a lot more. They think that there's a lot more matter than what you can see. The stars are regular matter. They seems like there's something called dark matter, stuff you can't see. We'll talk about that later. They say that about half of stars, they think, are born in double or triple systems like Alpha Centauri. Our star is by itself, the sun's by itself. But a lot of stars revolve around each other, so we just have to be one that doesn't. There are these things called globular star clusters where there could be hundreds of thousands of stars that all orbit each other. They can't just be sitting still because gravity would suck them together. But there are these things, these big, there's about 200 of them. This one they think has 250,000 stars. There's a couple hundred of these in our galaxy. These globular, because like a globe, so they're globular really, but everyone says globular, it should be globular. Star clusters, big huge groups of these stars. We'll talk about those later too. They're pretty awesome. You can see some with a telescope. And we say, okay, things don't last forever. They think our sun's been around, it's about 4.5 billion years, and that it's got another 4.5 billion to go. So we're like halfway through. The sun's got about halfway through its life. And we'll talk about that when we study the sun more. Okay, so the universe is big, but we're not the only galaxy. It used to be, Edwin Hubble was the first one that discovered that we're not the only galaxy. It used to be they thought the galaxy, the Milky Way, was the universe. The universe was this Milky Way we lived in. And then they realized, no, wait, Edwin Hubble took a lot of pictures of these faraway, blurry things. They called them nebulas, because nebulous means unclear. And so they are these unclear things because they didn't have very good telescopes. Well, Edwin Hubble got the best telescope in the world in the 1920s, and he took really good pictures. He was really good at taking pictures of these little nebulous objects, discovered that there are other galaxies like our own. Suddenly the universe got a lot bigger. We weren't the universe. The Milky Way is not the universe. There's lots of Milky Ways out there. There's lots of galaxies out there. The closest ones to us that you can see really well. There's like one little tiny close one that you can't really see. But the closest ones you can see really well, you have to go to the southern hemisphere to see. That's these two here, these two little smudges in the sky. If you go down south, you can see them really well. They're called the Large Magellanic and the Small Magellanic Clouds, because Magellan, the famous explorer a long time ago, he first talked about them. Because you got to go south to see them. People in Europe and stuff never saw them. Now, other people down south saw them, but they didn't write about it. They're not part of the Western world, so they call them the Magellanic Clouds, these galaxies. Kind of not fair, but oh well, that's the way it goes. So these things here, those are close galaxies, but they're not very big. Okay, the closest big galaxy to us is this one, and we can see it with the telescope. It's called the Andromeda Galaxy. It's a little over 2 million light years away. This is another little tiny galaxy that orbits around it, just like we have the Magellanic Clouds. They have this one here. I think there's a couple other ones, like maybe that one. So this is called the Andromeda Galaxy. Okay, you should know, we'll talk about the Andromeda Galaxy a lot because it's really cool. The Andromeda Galaxy, it used to be called the Andromeda Nebula before Edwin Hubble discovered it as a galaxy. It's a little over 2 million light years away. I just always say 2 million light years away, light years distant, which means when we look at it, like this picture probably wasn't taken that long ago, that's what it looked like 2 million years ago. We're seeing as it looked like 2 million years ago. Who knows what it looks like now? Probably about the same, but we don't know. We can only see what it looks like 2 million years ago. Now here's a really cool thing. If let's say there's a little planet here and they're looking at us, they're looking at the Milky Way, they'd say, oh, there's the Milky Way. It's the closest large galaxy to the Andromeda Galaxy. Now, they probably don't call it the Milky Way, but they see us 2 million years ago. So they'd be looking at the Earth as it looked 2 million years ago. They had a really good telescope. These Andromeda people could be looking at the Earth and see what it looked like 2 million years ago. Wouldn't that be awesome? So I really hope that they take a video of it and then they send it to us. And then we can see what happened 2 million years ago. However, let's say they send it to us with radio waves. It would take 2 million years to get the video. So unfortunately, just doesn't, the speed of light being a constant, can't go faster than light. The fastest they could get it here would be 2 million years. So maybe our ancestors will be able to watch the video. Not us. This is always a catch, right? It's always a bummer. Okay, Andromeda Galaxy. It's also called M31. because this guy named Messier, this French scientist in like the 1800s, this French astronomer, he was looking for comets because comets were cool. And he had one of the best telescopes of his day. And he spent all his nights looking in the sky for comets. And when he found something that wasn't a comet because it didn't move, is always there, this nebulous object, he gave them numbers. And then now he didn't call them Messier numbers, but now they do. Messier's number 31. So this is the 31st one that he saw. I believe there's actually I have a poster of him in my class here. You can't see it, but there are 110. There are 110 Messier objects. It goes from M1 to M110. And they're kind of the coolest things to look at because if he could see them with a not-so-good telescope, we can see them with not-so-amazing telescopes. Right? We don't need the Hubble telescope to see them. So Messier objects, those French objects, they're really cool things to look at. He labeled 110 of them. Then he knew that they were there, and he knew they weren't comets. So if he found another one, like, oh, maybe that's a comet. Okay, so this is M31, the 31st one he saw, the Andromeda Galaxy. Pretty cool. All right, so that's all stuff you should know. Moving on here. What else should we know here? So much good stuff. Yeah, the Andromeda Galaxy is they think a little bit bigger than the Milky Way. Okay, then there are a bunch of other galaxies. Okay, we live in what's called a local group. Not a very good name, right? Local group. Couldn't they come up with a fancier name than the local group? But that's what they call it, this local group of galaxies, which is about 50 galaxies. Okay, so we live in the local group. We should write that down, remember it. Local group. It's about 50, and they say about because there's a lot of little ones. So I can put a squiggly there, about 50 galaxies. They're the ones close to us, including those Magellanic Clouds and Andromeda, and the little one going around Andromeda, and there's some other little ones and big ones. Do you count that one? You can even see it. So it's about 50. You can't really say exactly. Okay, so we live in a local group of galaxies. Now, there are lots of groups, local groups. There's other local groups. This one is called the Fornax cluster of galaxies. So we live in a cluster of local groups of galaxies, something like this one. And then some clusters gather together in superclusters. So it says a local group is part of a supercluster of galaxies called the Virgo supercluster. Okay, so we're like a little cluster, and there's lots of little clusters. So we live in a supercluster. So the local group is a cluster of galaxies. And we live in a supercluster called the Virgo supercluster. So Virgo supercluster, that's our home. So if an alien comes to your house or sends you a message, asks you where you live, you say, oh, I live on a planet, the third planet around the sun. The sun is part of the Milky Way galaxy. The Milky Way is part of the local group. The local group is part of the Virgo supercluster. And then there are groups of superclusters, and there's big, huge spaces like that too. But that's kind of about as good as we could say about where we live. I think that there are some big webs of superclusters. You could go further, but we'll go over that stuff later. This is good enough for now. Okay, they talk about quasars. You can read that on your own. Some numbers you should know. We'll talk about the science of this, excuse me, a lot. But some numbers you should know is they think that the solar system, including the sun, the Earth, the sun, everything in our solar system, the older things in our solar system, they think is about it's about 4.55 billion years old. And that's why you hear 4.5 or 4.6, because it's a 4.55. Do you round that up to 4.6? Do you just say about 4.5? Either one works on a test. I take either one. 4.55 billion years old. Okay, that's how old they think our solar system is. The universe, they think, and we'll talk about this in detail, why they think this. It started with this Big Bang. They think the universe is older than that, of course, right? It's got to be older than the solar system. It's about 13.8 billion years. So about 3 times older. 3 times older than the sun. The entire universe is about 3, because 3 times 4 is 12. That 3 times 4.55 is 1.5. So pretty close to about 3 times older than our solar system. Those are numbers you should know, just to keep in mind. We'll talk about how they get those numbers. They don't just randomly come up with them. There's all kinds of data for it. They keep changing them. They get better and better data. Sometimes a little while ago it was 13.6, and they got some better measurements. They get better telescopes. They can get better data. But it's getting pretty set at like about 13.8. The next decimal place is where they start arguing now. They're pretty sure about the 13.8. Okay, those are numbers you should know, just to know something about the universe. All right, so what else here? Let's see if we can get through this. What am I at here? 25 minutes already. This time goes so fast. Again, you can pause this video. Okay, they talk about the universe as small. They talk about atoms and stuff. I'm not going to go over that so much now. About the sizes of things, and we'll go over that stuff later, so we can skip this here about atoms, and you guys are taking chemistry. Okay, so they talk about now that's kind of like, again, the universe as a whole. This is some cool stuff that Carl Sagan came up with. He talks about one of the videos to watch. So let's say, imagine, this is just to talk about the scale of things. It's kind of cool. Imagine the universe started here, which again, they think it did start. It wasn't around forever, they don't think. So Big Bang, right? Started January 1st, New Year. Then the Milky Way formed somewhere in May. In September, our solar system formed, right? We're about 1/3 the age of the universe. Then Earth's atmosphere becomes oxygenated in October because the plants put oxygen in the atmosphere and everything. And then the first complex life forms in November. We're not around yet. Now let's look at December. So December, they broke up into more detail. So if the universe starts in January, December 19th, things with backbones occur. Land plants appear here. So these are water plants that put algae and stuff in the plankton in the ocean that put oxygen in the air first. Dinosaurs, December 25th. Mammals, December 26th. Humans, December 31st. On the last day of the year, if you break up time into a whole year, the last day is where humans appear. And actually it even gets, we're like in the last seconds and stuff, as they say, how that works exactly here. This is the cosmic calendar. The invention of the alphabet doesn't occur until the 50th second of 1159 on December 31st. So humans haven't been around long, they don't think, right? That's the gist of that. So, okay, and that's the end of this chapter. There are a few things that we kind of skipped over that you should know. Let's see. If you took the sun, okay, here's another way to think about the solar system. You guys watched a video on it, hopefully, or you will. But let's say the sun was the size of about a grapefruit, about this big. That was the sun. Okay, then Jupiter would be about the size of a marble. Okay, so pretty big. Jupiter's a big planet, and the Earth would be about the size of the ballpoint of a pen. So imagine a ballpoint pen. Look at the little round ball in there. That would be the size of the Earth compared to the size of a grapefruit, or in other words, about 109 ballpoints. You took the 109 ballpoints. That would go across to be about the size of the sun, which would make it about a grapefruit size, 109 ballpoints. So again, this is the way to think about the scale of things. That's kind of cool. Let's see what are some of the things I want to make sure to mention. So yeah, I think we kind of talked about a lot of the main ideas here. There's a lot of ways that I think they went over one of the videos and things, but that we're moving through the universe, right? We feel like we're still. They used to think that the Earth was still, right? Everything goes around the Earth because it doesn't feel like we're moving, but that's because we don't. If you move in a straight line, you can't tell you're moving. That's one of Einstein's theories of relativity, that one of the basis of his general theory of relativity. You move in a straight line at constant speed, you don't accelerate, you can't tell you're moving. And we go in a circle around the sun, but it's such a big circle, it feels like a straight line. So they used to think, and again, and because we go in a circle, we spin every 24 hours, but it's a big Earth, and it's almost like we're going in a straight line, right? If you look at how you're spinning, it looks like a straight line. So it sure doesn't feel like we're moving. So they used to think we didn't move, but we do. We go in a circle. Every 24 hours as the Earth spins, we go around the sun at about a little over 60,000 miles an hour. The sun doesn't stay still. The sun moves within the Milky Way. It kind of bobs up and down in the Milky Way, and it circles the Milky Way. I believe it's about every 230 million years we orbit the Milky Way. So if the sun's orbiting it, we are too. We follow the sun. So we follow the sun around the Milky Way, and the Milky Way itself is moving relative to the other galaxies. We're actually heading towards the Andromeda galaxy. So the Milky Way is moving, the galaxies move. So we are moving in all kinds of ways, at all kinds of speeds. We're certainly not staying still, even though it feels like it, because it's mostly a straight line. Even though we're going in a circle, it feels like a straight line, and we're not speeding up or slowing down. So, okay, so that's cool stuff to know. And gosh, I think that's all I wanted to go over right now. So that's pretty cool. So I kept this a little bit shorter than the last one, I think. Well, okay, let me go over one more thing. When we talk about the Milky Way, okay, the Milky Way is this big spiral mess of stuff, but the middle is called the bulge. So there's like a big bulge in the middle, and the halo is the area around the top and the bottom of the Milky Way. So that's called the halo. And you'd have to send a spacecraft way up here in the halo to take a picture of the Milky Way. That would take a really long time, we talked about, so that's probably not going to happen. And if the Milky Way, if the universe is about 13.8 billion years old, 13.8 billion years old, okay, that means that light cannot have been traveling for more than 13.8 billion years, because light's only had 13.8 billion years to travel. Light always goes the speed of light, so there's not a single light ray that can have traveled more than 13.8 billion light years. Okay, so 13.8 billion light years is the longest a piece of light, a photon of light, can travel. It has that time to go more than that. Therefore, if we see something, the longest that light ray could have traveled is 13.8 billion years. Therefore, nothing can be further away that we can see than 13.8 billion light years. One of the videos I have you watch talks about how big the universe is, and that's the number they come up with. But now the universe can be bigger than that, but the universe that you can see with your eyes, or at least, yeah, you can't see anything light that has traveled more than 13.8 billion light years. So the furthest things you can see with the telescope have to be a little bit smaller than that, because it's hard to see all the way to the end. Maybe, I think the furthest things they've been able to see now are maybe 12 billion light years away with the huge telescopes, and they're really fuzzy and really hard to tell, and they argue about it and try to get better data and everything. But that's all because of the finite age of the universe, 13.8 billion years old, which means light cannot be traveling longer than 13.8 billion light years, so we can't see anything further than that away, and it's kind of hard to see that far away. You'd see the beginning of the universe if you could see that far away. You'd be seeing the Big Bang. Now you can see, they think, radiation left over from the Big Bang, called the microwave background radiation. We'll talk about that later, but that's not visible light. It's actually radio waves, because the visible light has stretched. They think that the universe started off small, right, and has been expanding, and space has been expanding with it, and that's a whole other story. There's so much good stuff to cover. Okay, I think now I'm finally done. Good. Hope you enjoyed the video, and I'll talk to you later.